we are going to cover how to design your parts so they're suitable for 3D printing. So, as we have seen up to now, even though there are certain limitations to 3D printing, we cannot overcome some of the problems with clever design technique. This is why it's important to be aware of some of the problems that you may encounter as we have discussed, so you can account for them in the design stage of your parts. This is called designing with 3D printing in mind. Okay, so as we've discussed, if you know that your part might have a tiny area in contact with the build plate, you can add a brim. If you know your part can be printed a certain way, such as upside down, you can orientate the part exactly that way in order to 3D print and avoid steep overhangs or sharp slopes, some of that to avoid the need for support structures. You can account for some of these issues during the design stage if you're aware of them. So you'll have less trouble when you actually come to 3D. A key property that we need to learn to define when 3D printing is infill. So what is infill? Well, pretty much we keep talking about these layers that we'll split our model into. Now, each layer, it won't be fully filled with material when 3D printing, yeah? Such as when you're using fused deposition modeling, we'd like to have a thick exterior or perimeter for each layer, because this will be the surface in contact, with the elements, with the outside, the surface that you touch and you see. But in the interior, if we were to fully fill it, of course, this would provide a strong structure. However, for most applications, if strength is not that important, if they're more for aesthetics or how it looks, or you need the part to be light, you don't want to fully fill it with material. Also, filling it with material uses up a lot of material because that's a huge surface area in the cross section. So what you would do is you'd fill it up to a percentage. Well, 100% infill, it means it's fully solid. It has material all throughout the cross section. And 0% infill means it's completely hollow. So it doesn't have any structure on the inside. It's just the perimeter. So a hollow section. Yeah. And depending on what value you set or you desire, between 0 and 100, you'll form a structural lattice, as you can see here, defined by this mesh, these tiny squares. That's the structural lattice, where you only deposit material along these lines, and the white spaces, that's just empty space where there's no material. And depending on how dense or how less dense it is, that defines the percentage infill. So pretty much with a lower infill, you use less material, but it's less strong. It has less of a structural consistency. Whereas if you go for 100% infill, or the higher the infill number, the stronger the part gets, but the more material you use and the heavier the part gets as well. So infill properties in 3D printing, it's similar, or it also has an effect on the print speed, the print structure. It's a similar property that you can affect, that you can modify, like the temperature you are melting your filament, the speed at which you set your build head to move at, so the layer building speed. But we also, considering the layer structure, we can choose many different infill patterns. It doesn't have to be the squares or the mesh that we've defined over here. This can be tiny little triangles joined up together, or tiny little circles. There are many different infill patterns that people have come up with and have, made available online. Certain infill patterns are predefined or pre-recorded in some slicing software. So when you prepare your 3D models for 3D printing, you can define infill pattern, infill density, and some other properties. We'll have a look at that later on when we cover slicing software. Yeah, but right now, all of these patterns, they don't have such a profound effect on the structure or the weight. There are certain optimizations that you can do, but more often than not, just having the simple plain rectangular infill is more, or rectilinear infill is more than enough for most applications. Now, let's move on to iteration. So, what is iteration? Well, pretty much when you design your first draft of a part that you want to build, maybe you even send it to be 3D printed. It comes back, or once you finish printing, you can see some mistakes that you made in the design or some optimizations that you could do, where you go back to the drawing board or you redesign the 3D model or edit it in a way. Then you come up with draft 2 of the model. You can send that to be 3D printed. If you're happy with it, you can keep it as the final draft, or you can go back to the drawing stage, make a few more changes, and so on and so forth, and end up with draft 3, draft 4, draft 5, whatever, until you're finally happy with the final model, and that's your final draft. Doing all of these drafts, that's what iteration is. That's the actual definition of iteration. Making several different drafts with tiny improvements in between until you reach a final model that you're happy with. In 3D printing, it is very common to iterate. So you come up with an initial design of a model, you test it, you go back, you redesign it. And many 3D modelers or people involved with 3D printing go through this process. It's a very common place to go back and edit your design to fix issues or add additional issues. Editing doesn't only happen when a print fails. So sometimes you have to go back to the drawing board because your design failed to be 3D printed, failed mid-print because of something that you might have forgot or not paid attention to, an issue that you need to fix, yeah? Sometimes you do it when you test prototypes. So you create a prototype part, you test it, yeah? And then you say, oh, okay, I've learned something from this part. I can make it better. I can improve it. Then you iterate and you create another draft of that part and you test it again, see how it performed. Maybe it has improved performance or it has deteriorated performance. It gives you a lot of data to learn from. So this is another example of when iteration might be useful. So as we discussed, iteration is going back and forth between printing and designing until the end product is satisfactory. Yeah. So pretty much when 3D printing, it is good practice to have several iterations, several versions, several drafts of a design. So you have that design history or development history, because when you make changes to your design, sometimes those changes might not work as you intend them to, or might not produce the results that you intended, and the previous version might be better. So it's always good to keep those records intact, to keep that design history, so you can always revert back to previous designs, just in case you need to. Or as an example, if you're designing something for a customer, you send draft 1, you send draft 2, you send draft 3. They say, actually draft 3 is not really what I like. I prefer draft 1. If you have all that record or that history saved, good file practice, you can easily go back to draft 1 and start from there, rather than having to redesign it if you got rid of draft 1. If you only keep one draft on your computer, that's not good practice. Now, let's move on to post-processing. We have discussed some of the tools and techniques that we use to overcome the limitations of 3D printing, such as support structures and Brims. However, using these techniques, we end up with additional geometry in the printed parts that needs to be removed. So, and as an example, in this case, where we had the table and we created the brim over here on the legs, obviously, once printing is finished, this is not the design that we actually want for the table. We do not care for this brim. We want it to actually be like this. previously, but we had issues printing it this way, and that's why we designed the brim to help print the end piece. So what would happen is after printing is complete, we'd have to trim away and remove this brim because it was just an assembly aid, an aid during printing, and it needs to be removed. So obviously you can trim this away with some pliers or some scissors, depending on what material used. You could sand it back if you wish to, but all of that adds time. You need additional tools. You used additional material over here. Maybe the surface finish after you file it or cut it might not be the best. You might also end up damaging your parts when you try to remove these structures or support structures as well. Then you'd have to reprint the part. So in essence, yeah, what happens is you need to try and think and design your parts in order to minimize the amount of post-processing that you need to do, yeah, in order to save time and material and costs and all of these, yeah. The more post-processing that you have in your manufacturing process, the less efficient it is. So similarly with removing the brims or the support structures, washing off the resin from SLA, stereolithography produced parts. That's also another example of post-processing, but that's intrinsic to the technology. You cannot print using SLA without having to wash off the resin. So you need to take account of these, the limitations of the printing technology you are using. We discussed that using selective laser melting or selective laser sintering, that technology doesn't need support structures because it's supported by the powder on each layer, in each layer. So if we printed, let's say, this table using selective laser melting, ideally we wouldn't even need the brims over here because it's supported on all sides as we build up with powder. However, if you recall our conversation on infill, where obviously the outside is completely melted is the perimeter, but what's inside is a structural lattice. Because you have powder everywhere, you'll also have powder on the inside of your legs and the main body of the table inside the structure. So obviously sometimes you might want to actually remove that in order to reduce weight of your part or something of the sorts. So what you'd have to do is you'd actually have to drill a hole or cut a hole in the bottom of your 3D printed part in order to remove all the collected metal filings or shavings or material powder from inside the part. Obviously, you could set the bottom layer as not being filled up, so you only do the perimeter of the bottom layer, yeah, and not the actual surface area. That way you have an empty hole at the bottom for everything to pour out. You could do that in the design stage. That will minimize the post-processing you need for drilling through the part to remove the powder material. Yeah. And lastly, obviously the one we discussed in depth was removing support structures and brims from fused deposition modeling printed parts. Yeah, all of these are examples of post-processing. Obviously, some post-processing can be reduced, can be minimized, such as support structures and brims. Others, such as washing off the resin from SLA printed parts, that you cannot actually get rid of or minimize because it's intrinsic to the manufacturing technology itself. Obviously, post-processing is very common in 3D printing, but we should try to use clever design techniques where possible in order to minimize this in terms of efficiency and cost and material usage.